this problem says a woman stands on a scale in a moving elevator. The photo I found in the book is, or the diagram is of that of a man standing in an elevator or well. Her mass is 60 kilograms, and the combined mass of the elevator and the scale is an additional 815 kilograms. Starting from rest, the elevator accelerates upward. During the acceleration, the hoisting cable applies a force of 9,410 newtons. What does the scale read during the acceleration? So let's see what kind of information is given. The mass of the woman is given, so 60.0 kilograms. The mass of the elevator with the scale, I just call it ME, is given as 815 kilograms. And let's see what else is given. It says that a force is applied of 9,410 newtons. I will call that tension, 9,410 newtons. And it says it's accelerated up. That means that the force also has to be up, so I consider it positive. And then it's the starting from rest, so V0 equals 0 meters per second. I write it down just in case we do need it. I suspect we won't, but I just write it down anyway. What it actually tells this one here, what it tells us is that, well, it's at rest, and then the acceleration is going to go up as the drawing indicates, as the problem indicates. So the elevator is accelerating up and going up. There could be still an acceleration when you're up, when you're going down, and that would be as you're going down, and the elevator would be decelerating. In that case, you also have an acceleration up. So either way, here they say, start from rest. Okay, as you can already see, I set up the problem into two parts, elevator and woman, and just the woman. And what gave it away is that we have two different masses given here, one for the woman and one for the elevator. And because there's only one mass in Newton's second law, that's why I split it up into a couple of problems. So let's see how far we get, or where we get with this. First of all, I'm going to write down Newton's second law. Maybe that should be second, because I should first identify what I have. So consider this actually be second here. On the elevator and the woman, what we have given is the weight of everything. That's a force. In fact, we should calculate the weight here very soon. And the combined weight as well. The total mass as well as the total weight. What we have given is the tension in the cable. So there are a couple of forces involved, both of which are given. Mass, the total mass is given, and then the acceleration. They don't ask for it, so I'm not going to make a question mark, but if needed, we could calculate it. Now, for just the woman, what we have given is her weight, but there's a second force acting on here, and that would be the normal force. I'm not going to call that the I'm not going to call it a tension, because the rope isn't attached to her. The rope is attached to the elevator. So that would be the normal force, and that indeed is what the scale measures. So that's what they're asking for. It says, what does the scale read during the acceleration? And when you look at the chapter, what a scale reads is not the weight. What it reads is the normal force that a scale needs to apply to you in order to keep you up. Now, for most cases, it happens to be equal to the weight, because weight pulls you down, normal force pushes you up. The two are equal out, except one of them is negative, so that you come up with a zero net force. But in this case, that's not the case, because there is a net force pulling up the entire elevator, including the woman. So the normal force in this case, we expect that it's going to be larger, because the woman is and the elevator is accelerated up. Okay, anyway, over here we also have given the mass of the woman, and we don't know the acceleration and we don't know if we need it, so I'm going to leave it blank for now. I'm just going to shift this box over to get a little bit more space. Okay, let me actually calculate these here. So the weight for the woman, so times 9.8 comes out to 588 newtons, and the weight is pointing down, so that's negative, and the weight for the elevator is 7,990 newtons. I didn't leave much space here, and of course that's also negative. This was, by the way, supposed to be an E for elevator. The total mass obviously is 875 kilograms, 3 significant figures, and the total weight comes out to, let's see, that's 8,580 newtons rounded, and that also would have to be negative. Okay, let's see now here from this Newton's second law for the elevator and the woman. We have the weight plus the tension. Of course, the weight will, once we plug in numbers, the weight is negative, equals mass times acceleration, where everything is given but the acceleration. For just the woman, we have, of course, sum of the forces equals mass times acceleration. And here we have the weight of the woman plus the normal force equals mass times acceleration. Okay, normal force is what we're supposed to solve for, normal force. So that equals mass times acceleration minus the weight. I'll comment on that in just a moment. Well, what we have now here is we don't know what the normal force is. We're supposed to figure it out. We know what the weight is. It's minus negative 588 newtons, and because I subtracted it from the right hand side, it's a minus negative, so that actually will be positive. It will be a positive number. And then what also we have given is the mass, but we don't have the acceleration, so which means we're supposed to calculate the normal force, but we don't have the acceleration. Well, that's where this first one here comes in from the elevator itself. This is where we can calculate the acceleration. So acceleration equals the weight plus the thrust divided by, and this one here should be the total mass, by the way. I should have written this one here as well. Total mass, total weight. Okay, that doesn't look very pretty the way I wrote it. So we have here the total weight of minus 8580 newtons, and here the tension. If I at some point said the thrust, I don't think I did. I meant tension, 9,410 newtons. Notice that this number is bigger than this one here, so we do come up with a positive acceleration, and that makes sense because the elevator is supposed to be accelerated upward. We take that positive acceleration, we plug it in here, times the 60 kilograms of the woman. We come up with a positive number, and then we add it to the weight, and again I said minus a negative number, so that's a positive number, and so overall this part here added to the weight of the woman will make the normal force larger, and that makes sense that when elevator accelerates upward that you feel heavier because there's more normal force pushing on you, because it has to not only counter the weight but it also has to accelerate you upward. So you will come up with a normal force here that is larger, indicating that your weight, so to say, has increased, which is actually a normal force.